pupil is smaller. An iris, the colored part of the eye, it's actually a muscle. The colored part of your eye is your eyes. I mean, it's part of the muscle in your eye that controls the opening of the pupil. The lens is a transparent structure located behind the pupil that actively focuses or bends light as it enters the eye. Imagine it as being a magnifying glass that focuses on the back of the eye, which is the retina. Accommodation is the fact that the lens actually changes shape to accommodate new light. The process by which the lens changing shape to focus incoming light so that it falls on the retina. Alright, so here we go. We've got the pupil here, light comes in, alright, it's focused on the back of the eye, which is the retina. Okay? The weird thing about it, so look at this, here's the distant object, boom, here it goes. It's actually upside down on your retina. Your brain does something amazing and it actually flips it right side up as it travels back into your occipital lobe. Now we have some normal vision here. You can see this. It is this leaf is actually placed completely and perfectly on the back of the eye. Nearsighted vision, the leaf is actually placed in front of the retina. It doesn't quite reach it. And then farsighted vision, the leaf would actually be projected like it would be farther back than the retina. And that's what makes people farsighted or nearsighted. So let's look at these true definitions for farsighted, nearsighted, and astigmatism. So myopia is nearsightedness. That is the technical term for nearsightedness. So distant objects appear blurry because the light reflected off the objects focuses in front of the retina. I suffered from this for most of my life, from 3rd grade until I was 26, and I got LASIK. We'll talk about that here in a second. So everything, and it's nearsightedness. I could see anything close, nothing far away. And whenever I say close, I mean really close. Anything farther than that, you know, I couldn't see. Unless I had my contacts in or my glasses. Hyperopia, farsightedness. Objects near the eyes appear blurry, so close by is blurry, because light reflected off the object is focused behind the retina. Well, we just talked about that. And then we have presbyopia, form of farsightedness during middle age that is caused when the lens becomes brittle and inflexible. As you get older, your sense organs don't work as well as they once did. Okay? Smell, hearing, sight, all of that. Yeah, they don't work as well as they did. They become brittle. They become old. They're used. I mean, think about it. What have you been doing your entire life? One thing that you've been doing your entire life, and that is sensing. Okay? From the moment you were born, you've been sensing. You've been using these sense organs for how long now? 15, 16, 17, 18 years? I've been using mine for 36 years. My parents have been using them for 60. And my grandparents have been using them for 80. And you can see through all of those ages how they deteriorate, right? How they get brittle, how they don't work as well as they once did. Because guess what? You've used them for a lifetime. Okay? So this is pretty much just having readers, right? I mean, you're going to go to the, Walmart, wherever, buy us a little reader so you can, use them as reading glasses. That's what presbyopia is. Astigmatism is an abnormally curved eyeball resulting in blurry vision for lines in a particular direction. A lot of people suffer from this. And then LASIK is reshaping the cornea so that light rays focus more directly on the retina. And this is reshaping the cornea, not the lens. But it's funny, I had this done. And they prescribe you Valium before, so it takes off the edge of the anxiety or whatever. But you sit there and you're on Valium, so you really don't care what's going on. And what ends up happening is you smell your own eyeball burning because the laser is lasering your cornea 250 times to reshape your cornea so it focuses light better on the back of your retina. And you can smell that happening. And it's weird. Immediately after you go, you get an eye test, and then boom, you're 2013. Okay? From being able to not read anything past this in front of my face, to perfect vision, more than perfect vision. It's unbelievable, modern medicine. All right, the retina. Pretty special place. Allows for some amazing things to happen for the human. The retina is a thin, light-sensitive membrane located on the back of the eye that contains the sensory receptors for vision. What are those receptors? Rods and cones. Rods are the long, thin, blunt sensory receptors of the eye that are highly sensitive to light, but not to color. They are primarily responsible for peripheral vision and night vision. So here we go. Boom. There's a rod. That's what it would look like. Here it is again. These are real rods. Here they are. Photosensitive chemicals at the very end, and then a nucleus closer to the retina. So yeah, peripheral vision. If you've ever noticed this, if you want to see in the dark a little bit better, don't try to focus directly on something. Focus a little bit to the right or to the left of it, and use those rods and cones, those rods, not the cones, to really pick up that sensitive, dim light in that object. Try it. Peripheral vision is better for night vision. All right, then we have cones, the short, thick, pointed sensory receptors of the eye that detect color and are responsible for color vision and visual acuity, the sharpness of the image. So seeing the fine detail. Here's the cone, obviously shaped like a cone, and you can see it here as well. The fovea is in the very center of the retina. It is where most of your cones are, so it's responsible for visual acuity, your focus on one particular object, and that's where most of your cones are, in the center of your retina. So a small area in the center of the retina composed entirely of cones, where visual information is most sharply focused. And then we have the optic disc. And that's where this information from the rods and cones leaves your eye and goes back into the back of your brain to the occipital lobe. So this is the area of the retina without rods or cones where the optic nerve exits the back of the eye. Right here. Okay? Here's the fovea. All right? And here is the optic disc. Something weird with the optic disc. It has a blind spot, the point at which the optic nerve leaves the eye, producing a small gap in the field of vision. So you actually can't see. If you only had one eye, there would be a blind spot for you. But we have two eyes, and our other eye makes up that information from that blind spot from the eye that we're talking about. So, if I'm looking at something right now with just my left eye, there is a blind spot, okay? And it's kind of angled in a certain direction. Same with this. It's almost angled like this, okay? Because there's a place in the back of my eye called the optic disc that there are no rods and cones, because it's, I have this thing that's as thick as a pencil leaving the back of my eye, going to my occipital lobe, crossing in the middle of my brain. So yeah, here we go. This is where the blind spot is, right? So here we are, boom, and then the blind spot for the left eye, blind spot for the right eye. But again, we get to make up this information. If you were here, we'd do this right now. We'd cover both eyes and see if I can make one of those disappear. All right, processing visual information. Visual information is processed primarily in the brain. However, before visual information is sent to the brain, it undergoes some preliminary processing. And that happens in the retina. So we have ganglion cells and bipolar cells. These are neurons. In the retina, and by the way, your eyes are actually a part of your brain. It's almost the only part of your brain that's outside of your brain that is exposed to the world. So the ganglion cells in the retina, the specialized neuron that connect the bipolar cells, the bundle axons of the ganglion cells, form the optic nerve. I'll show you an image here in a second that's going to put this into a better perspective. And then the bipolar cells in the retina is the specialized neurons that connect the rods and cones with the ganglion cells. Let's look at the image. So here we go. Incoming light right here, and this right here is the retina. So we have the ganglion cells here, okay? And those are connected to the bipolar cells, which are connected to the rods and cones. So purple are bipolar cells, and they are pretty much transducing some sort of information almost immediately from the rods and cones to the ganglion cells. The ganglion cells are the actual things, so axons are leaving these cells and forming the optic nerve that is actually exiting the eye. All right, from eye to the brain. So how is information transmitted from the ganglion cells of the retina to the brain? The 1 million axons of the ganglion cells are bundled together to form the optic nerve. The optic nerve is the thick bundle of neurons, or nerves, that exits the back of the eye and carries information to the visual cortex in the occipital lobe. It's the same diameter as a pencil, which is interesting. I don't know, it's probably not always that thick, right? But as you get older and you use it and you increase the transmission speeds of this ability of a human, it gets thicker and thicker and faster, right? It has to be myelinated. Optic chiasm. So the point of the brain where the optic nerve fibers from each eye meet and partly cross over to the opposite side of the brain, here. And they cross over, okay? Again, your left eye is processed in your back right brain. All right, color vision. So this gets a little confusing, so stay with me here. First things first, color is not a property of the object, but a sensation we perceive in the brain. Okay. Do objects out there in the real world put off wavelengths or color wavelengths? 100%, right? It reflects the color. You learn about this in biology and physical science and all that kind of stuff, I think. Physical science probably more than anything. But color is a perceptual experience, as in it exists inside of your brain. Nowhere else. All right? You are perceiving color. You're not perceiving my color. I'm going to see things that are just slightly different than you possibly, okay? So the perceptual experience of different wavelengths of light involving hue, saturation, and brightness. Hue is the property of wavelengths of light known as color. Different wavelengths correspond to our subjective experience of different colors. So this is just the, different shades of blue, if you will. Saturation, the property of color that corresponds to the purity of the light wave. If the light wave is pure, then you're going to see its true color, its true saturated color. And then brightness, the perceived intensity of a color, which corresponds with the amplitude of the light wave. So a person with normal color vision can discriminate from 120 to 150 color differences based on differences in hue and wavelength alone. When saturation and brightness are factored in, potentially we could perceive millions of different colors. Just check out filters on Instagram or Snapchat or anything like that. You can see this in real time. All right, how we see color. We got two theories. Both of them are right. So that's one of these things in psychology, right? That two theories explain something on a different level every single time. Emotion is like that. So here we go. Trichromatic theory of color vision. This is the theory that sensation of color results because cones in the retina are especially sensitive to red light. That would be long wavelengths. They're also sensitive to green light, medium wavelengths, or blue light, short wavelengths. This is brought up by Hermann von Helmholtz. So what proves this is color blindness. So one of several inherited forms of color deficiencies or weaknesses in which an individual cannot distinguish between certain colors. This is whenever your cones have malfunctioned. That's what color blindness is. Happens in males a little bit more than females. Not a little bit, a lot more. Yeah, I don't know. It's a genetic problem. Okay? Opponent process theory of color vision. So the theory that color vision is the product of opposing pairs of color receptors. Red, the opposite of red would be green. The opposite of blue would be yellow. And the opposite of black would be white. This is the opponent process theory of color vision. When one of those is present, the other one is dormant. So when I see red, I am blocking green. When I see blue, I'm blocking yellow. When I see yellow, I'm blocking blue. When I see green, I'm blocking red. Let's take a look at this, okay? An after image is what proves this. So a visual experience that occurs after the original source of stimulation is no longer present. We're going to mess around with that in a second. So here's the opponent process theory again. So red, green cells increase firing when red is present and decrease it when green is present. Same with yellow and blue. So let's look at what an after image is. It's a sensation that lingers after the stimulus is removed. All right, in the following slide, I want you to fix your eyes on the dot in the center of the flag. You can blink if you want to, but I want you to stare at the dot for 30 seconds. Here we go. Here's the dot. Start staring now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. What do you see? You should have seen the American flag in its true colors. These are the colors opposite, right? Opponent process theory says the opposite of yellow is blue. The opposite of black is white. The opposite of green is red. Whenever you stare at this image for a long time and stare at it intently in the middle, and all of a sudden, boom, it's taken away, you see an after image of its opposite colors. This is what proves the opponent process theory. Okay? Here's some different things when it comes to color blindness. This is a normal person's vision. This is protanopia, so red-green color blindness. So obviously red and green are taken away and everything gets a little jumbled up here in the middle. Deuteranopia, red and green color blindness again. So, and then tritanopia, blue and yellow color blindness. So, you know, and this is what it would look like in a normal cartoon. Okay, so here we go. Boom, normal, protanopic, deuteranopic, and then tritanopic. So, and here's an example of something that you, if you're colorblind, then you're probably not going to see the number 17 right there, right? So, and if you have trouble seeing it, squint a little bit. All right, integrated explanation of color vision. So let's talk about it. How can both theories be right? It turns out that each theory correctly describes color vision at a different level of visual processing. As described by the trichromatic theory, the cones of the retina do indeed respond to and encode color in terms of red, green, and blue. But recall that signals from the cones and rods are particularly processed in the ganglion cells before being transmitted along the optic nerve. Researchers now believe that an additional level of color processing takes place in the ganglion cells. As described by the opponent process theory, the ganglion cells respond to and encode color in terms of opposing pairs in the brain. The thalamus and visual cortex also encode color in terms of opponent pairs. So trichromatic theory says something happens right immediately whenever the light hits the cones, and opponent process theory says in this processing that we do as it travels, you know, through the brain, there's some sort of processing of color there as well that uses opposing pairs. All right, hearing. We're going to call hearing audition, okay? The technical term for the sense of hearing. So auditory sensation or hearing results when the sound waves are collected in the outer ear, right here, the pinna, right? The fleshy, cartilagey feeling of the ear. Amplified to the middle ear, right? So it goes into the hole, hits the eardrum, and converted into neural messages in the inner ear, all right? Where we would see things like the basilar membrane, all right, and the cochlea. So what we hear, the nature of sound, we actually hear sound waves, right? So my voice is producing sound waves right now. They're probably coming through your speaker. They're coming through something, right? Maybe your headphones. Sound waves are the physical stimuli that produce our sensory experience of sound. Our perception of sound is directly related to the physical properties of sound waves. So here you go. This is that's one small step for man, one giant leap for mankind. That's what these sound waves actually look like. And they actually enter into your ear. A physical stimulus. All right, loudness. The intensity or amplitude of a sound wave measured in decibels. Okay, loudness. Amplitude is interchangeable with loudness. The intensity or amount of energy of a wave reflected in the height of the wave. So the amplitude of a sound wave determines the sound's loudness. Amplitude and loudness are going to be interchangeable. Decibel is the unit of measurement for loudness. Pitch is the relative highness or lowness of a sound determined by the frequency of the sound. And then frequency, the rate of vibration passing a certain point per second. And then timbre is the distinctive quality of a sound determined by the complexity of the sound wave. This is a hard thing for anybody not musically inclined to understand. I'm not musically inclined. It took me a while to figure this out. It's the purity of the sound. Does it sound like it's supposed to sound? Right? When I hit the note, am I hitting the note correctly? That's kind of what it is. Okay, so is it sounding true? Does it sound like an oboe? Does it sound like a trumpet? All right? In its pure form, it should. This is just some examples of decibel levels. Food blender, gas lawnmower, somewhere around 90 to 100. That's, pretty loud. Rock band, all right, I've had the pleasure of seeing Kiss twice. One time I saw them about 5 rows back, and my ears were ringing for days afterwards. I didn't have eyebrows afterwards because the pyrotechnics of the show burnt my eyebrows off. You wanted the best, you got the best, the hottest band in the world, Kiss. Sorry. All right. How we hear, the path of sound. So we have the outer ear. So the part of the ear that collects sound waves consists of the pinna, which is that outer ear right here. The ear canal, which is the hole, right? And the eardrum. The first thing that the sound waves really hit as it enters the ear. So it's a tightly stretched membrane at the end of the ear canal that vibrates when it's hit by sound waves. Then we have the middle ear. This is the part of the ear that amplifies sound waves, and it consists of 3 small bones, the hammer, the anvil, and the stirrup. We'll take a look at these things in a little bit. They literally look like those things, that's why they're called those things. The stirrup transmits the sound onto the oval window, and that separates the middle and the inner ear. And the inner ear is where the magic happens. This is the part of the ear where sound is transduced, where the sound wave is actually changed into an electrical neural impulse. So this consists of the cochlea and the semicircular canals. The cochlea is the coiled, fluid-filled inner ear structure that contains the basilar membrane and hair cells. It looks like a seashell or a cinnamon bun, so it actually it kind of goes round and round, and kind of like it looks like it's funneling, sound waves somehow, some way.